is exam 3 for fall 23, chapters 5, 6, and 7. First, I have this conservation of energy problem. Has a speed of 4 meters per second up here at the top, and I want to know so at point B it has 6 meters per second. It's going faster now. What is the height at point B, and then what is the velocity at point C? So recognize that here it has both kinetic and potential energy. That's true here too, that it has kinetic and potential energy, but down here it just has kinetic energy. So let's first start with this. I would say that the energy here is equal to the energy here. So that's 1/2 mv squared plus mgh. That's all at point A is equal to 1/2 mv squared plus mgh. That's all at point B. All right, notice my masses, they all cancel. It's a good thing. And so I have 1/2 of VA, that's 4 squared, plus 10 times the height there, which was 8 meters, is equal to 1/2 of 6 squared, plus 10 times the height at point B, which is what I want to know. It's 8 plus 80 minus 18 divided by 10 is equal to HB. 88 is equal to 7 meters. 7.0 meters, which makes sense because I know that it should be lower than it was here. It is going faster, so that makes sense. Now, what is the velocity at point C? That's part B. Very similar question. I'm just setting that original energy, 1/2 mva squared plus mgha, is equal to the kinetic energy at point C. That's cancel. 1/2 of 4 squared plus 10 times 8 meters is equal to 1/2 of VC squared. 88 times 2, 176. I get 13 meters per second, which again makes sense because it should be going faster than it is here. All right, consider this block that is initially at rest at the top of this inclined plane. If the inclined plane is frictionless, what is the speed of the block at the bottom? So for part A, I know that any potential energy, it's at rest, so it only has potential energy, has to be converted to kinetic energy. So the potential energy at the top is equal to the kinetic energy at the bottom. That's mgh. H is going to equal to 3, is equal to 1/2 mv squared. The m's cancel. I get 10 times 3 equals 1/2 v squared. 30, 15. V is equal to the square root of 15. It's 3.9. Now, I have this frictional force as this block moves down. I have a frictional force of 4 newtons that takes energy away from that object as it moves across this distance. I'll call that D. That's equal to 5 meters. This is a 3, 4, 5 triangle. The square root of 3 squared plus 4 squared is equal to 5. So the way I'm going to think about this is the potential energy that it has at the top minus the work that's done by friction is equal to the kinetic energy at the bottom. There are other ways that you can think about it too, but I have this total amount of potential energy. I take away that work due to friction, and then that's equal to the kinetic energy. So that's mgh minus the frictional force times the distance over which it acts is equal to 1/2 mv squared. Sorry. So I think I have m right. Yeah, 10 kilograms times 10 meters per second squared times the height, that was 3 meters, minus the frictional force, which is 4 newtons, times the distance, which is 5 meters. I should have 2 sig figs in all these. Is equal to 1/2 of 10 times v squared, which is what I'm looking for. I'm going to come up here and do this. So that's 300 minus 20. That's 280 divided by 1/2 of 10. Take the square root of that. I get 7.5 meters per second, which that's not right. So let's address this again. Made some mistake here, so let's see what that mistake is. I'll pause for just a second. Okay, so I saw my mistake. My mistake was not in part B, it was part A. But I do want to just point out here why I knew that I had a mistake. Is because I found this velocity to be bigger than what I found over here, and that just can't be right. It should be going more slowly. So really my problem here is with this. Let's correct that. Here I'd said 10 times 3 is 30, and then I took half of it, but I really should have been dividing by half. So this should be the square root of 60 instead of the square root of 15, and the square root of 60 is 7.7 meters per second. And then all is right with the world. But notice how I checked my answer, and I knew that one of my answers must have been incorrect. So if you'd made this mistake, I would have counted off half because you'd made this algebra mistake right here. All right, here I have a collision. It's a perfectly inelastic collision. That just means that they stick together, and energy is not conserved. And I want to know what is the initial velocity of V2. Or, let's see. So I'm asking for the total momentum of the system, but I can't find that until, well, I can actually. Let's do that because I know the mass of this, which is 6 kilograms. So I know everything about this system. So the total momentum is equal to m1 plus m2 times 6 times v final. That's going to be 6 kilograms times 6 meters per second, negative 6 meters per second. That's equal to negative 36 kilogram meters per second. All right, so that's the total momentum. This is a little bit different than the previous problem that I'd given in that I think previously last semester I had this velocity was known and this velocity was not known, but nonetheless, same way to approach it. Now I want to know that initial velocity, so I say that the initial momentum is equal to the final momentum. That's going to be 2 kilograms is 4 meters per second plus 4 kilograms times V2I, and then that's equal to, well, I've already found this, the total momentum, negative 36. So just exactly what I did in part A. So that is equal to 8 plus 4 V2I equals negative 36. Negative 36 minus 8 divided by 4. What's that? Negative 44 divided by 4, or negative 11 meters per second. That is to the left. Either negative or to the left, but notice here that I have, what was it, negative 11. I have velocity that is equal to 11 meters per second to the left. It has to be to the left, right, because the net momentum of this system is to the left, but the momentum of this particle is to the right, so the other particle has to be moving to the left, and it needs to be moving to the left at a pretty good clip, actually, in order to overwhelm the momentum of this particle and make them all move to the left. All right. I have around the world with a yo-yo. I give its omega is 4 radians per second. That's in SI units, I don't need to do anything with it. The mass is 0.10 kilograms, and the radius is 1.0 meters. First, I just want to know what is the centripetal acceleration. This is equal to v squared over r. I'm not giving v, I'm giving omega, so I can just say omega squared r. That's equal to 4 radians per second squared times 1 meter. That's equal to 16 meters per second squared. So that's my centripetal acceleration. And I want to know now, what is the tension in the string at the top of the yo-yo's path? So as this yo-yo travels around, notice that there are two forces acting on it. There is a force that is the weight, that's Fw, and then there's also the tension, F tension. The combination of these forces give the centripetal force. And then also recognize that the acceleration at the top is in the downward direction, so it's negative. So I can say that the sum of the forces in the y direction is equal to may. Sum of the forces in the y equals negative Fw plus Ft. Actually, these are in parentheses. Both of these are negative. Is equal to the mass times the negative. I'm going to label this as a negative AC because it has a magnitude of 16 meters per second squared, which I've already found, but it's in the negative direction because it's always towards the center of the circle. All right, so the effect of that is that both of those negatives go away. They cancel one another out. I'm looking for the tension, so I'll just solve this for the tension. That's going to be MAC minus the weight is going to be 0.1 kilograms times 16 meters per second squared minus the weight. Let's see, the mass here is given, so I can find the weight is equal to m times g, or 0.1 times 10, or 1 newton, 1.0 newtons. So that's equal to 1.6 minus 1.0 is equal to 0.60, no, I guess it'd be 0.6, excuse me, newtons. All right. Notice here that if instead of being at the top, it was at the bottom, then the centripetal acceleration would then be positive, and it would change this problem. If it were at the bottom, then I would find that the tension would be equal to 1.6 plus 1.0, or 2.6 newtons. There's a bigger tension at the bottom than there is at the top. We did a problem like that. That's the Ferris wheel problem we did in class. All right, block has a mass of 2 kilograms and slides across the floor and encounters a rough patch. Coefficient of friction is 0.2. So let's see, mass is 2.0 kilograms. Mu is 0.2. Um, it travels a distance, I'm going to call that d, of 9.0 meters before stopping. And I want to know what is the block's initial velocity. So our governing idea here is that it has a certain amount of kinetic energy to start. It loses all of that energy by the work due to friction. And so when it loses all of that, it has a final kinetic energy of 0. Okay? So that's 1/2 mv squared minus the frictional force times the distance is equal to 0. Or you can just say that the kinetic energy is equal to the work done by friction. All of that kinetic energy is taken away by the frictional force. I need to know what is the frictional force. I know that F is equal to mu times the normal force. That's going to be 0.2. Okay, so the frictional force is mu, which is 0.2 times the normal force. But remember, the normal force is equal to the weight. So that's going to be 2 kilograms times g, or 20 newtons. So that's 0.2 times 20, that's 4 newtons. So now I have everything in place. I want to know its initial velocity. I have 1/2 of the mass, that's 2.0 kilograms times v squared, minus the frictional force, which is 4 newtons, times the distance, which is 9 meters, and that's equal to 0. This half of 2 is 1, so v squared is equal to the square, or excuse me, v is equal to the square root of 4 times 9, which is 36, or 6.0 meters per second. So A is the right answer. Which of these basic units for kinetic energy? That's 1/2 mv squared. I forget about the half. That's going to be kilogram meters per second squared. So kilogram meters squared per second squared. looks like B is the right answer. A block falls from a certain height onto a spring. The spring constant of 10. The spring compresses. What is the initial height? So initially, this object has potential energy, and there's a spring down here. But then it compresses the spring, and all of that potential energy, which is gravitational, becomes elastic potential energy in the spring. So I say mgh is equal to 1/2 kx squared. I'm looking for h, so it's 1/2 kx squared divided by mg. That's equal to 1/2 of k, which is 10, times x squared. It compresses by 2 meters, divided by the mass, which is 2.0 kilograms. This is the 2.0 meters, times g. Those cancel. It's 1/2 force, so it's equal to 1 meter. Here, what is the work done by this guy? This is the only force. Actually, no, there are other forces, right? There is the weight of the object, the normal force of the object, but both of those forces don't do any work because they're not in the direction of the displacement. They're perpendicular. No, the work done is equal to work FD cosine theta. That means the x component of this force. There is a y component, but it doesn't do any work. So that's going to be 30 newtons times the distance, which is 5 meters, times cosine of 60. 150 cosine of 60, 75 joules. Push a block along a horizontal surface with a horizontal force of 12 newtons. Experiences a kinetic frictional force of 4 newtons. You push the block a distance of 3 meters, but how much has the energy of the block increased? Two ways you can think about this. I can take the work of your force minus the work done of the frictional force, and that will equal to the final kinetic energy. That would be the work of the force is 12 newtons times 3 meters minus 4 newtons times 3 meters equals the change in kinetic energy. It's 36 minus 12. So that's the answer. Or I could say that the net force, 12 newtons, 4 newtons, the net force is equal to 8 newtons, and then the work done by that is F times D, which is 8 times 3, which is also 24. Box slides toward you and you stop it. Which of these statements is true? The energy of the box has changed. That's true. It had kinetic energy and now it doesn't. You applied a conservative force. That's not true. It's a contact force. It takes energy away. You did positive work on it. No, I did negative work. You caused the box to accelerate. Yes, I gave it a negative acceleration, but I caused it to accelerate nonetheless. So D is the right answer. Here, car goes from rest to 50 and then 50 to 100, which requires more energy. If I think about the kinetic energy and how it relates to V, remember kinetic energy is equal to 1/2 mv squared. It's a parabola. So as I move from 0 to 50, I just use this much energy. But as I go from 50 to 100, I use this much energy. It takes a lot more energy to go higher speeds. A box is being pulled across a rough floor at a constant speed. What do you say about the work done by friction? That's negative work. All right, now we're getting into collisions. So this is momentum. 2-kilogram block is traveling to the left at 3 meters per second. Let's draw a picture. That always helps me. A 2-kilogram block is traveling to the left at 3 meters per second. It collides with a 1-kilogram block traveling to the right at 4 meters per second. That's the initial. Now the 2-kilogram block travels to the left at 2 meters per second, so it's going more slowly. and I want to know the final velocity of this 1 kilogram block. All right, so I say 1 times 4 plus 3 times 2. Actually, I'm sorry. 1 times 4 is 2 times negative 3. It's going to the left. Is equal to 1 times VF plus 2 times negative 2, because it's traveling to the left. It's 4 minus 6 equals VF minus 4. That's 2 meters per second. It's going to be to the right, as it should be, yeah, so it's positive. A raft with a mass of 100 kilograms is drifting. Is drifting at 4 meters per second. I don't give you the direction, we'll just assume to the right. And a person jumps onto it. Yay! Jumps onto the raft, and I want to know what is the speed of the raft after the person jumps on. So initially my momentum is 100 times 4. But in my final state, this is a perfectly inelastic collision. I've now doubled that mass, and I want to know what the final velocity is. So that's 400 divided by 200, or 200 meters per second. 2 meters per second. All right, an object with a mass of 2 kilograms accelerates from 8 to 16. So delta V is equal to VF minus VI. That's going to be 16 meters per second minus 8 meters per second, which is equal to 8 meters per second. Okay, what forces caused this? I know F is equal to delta P over delta T. That's M delta V over delta T. That's going to be 2 kilograms times delta V, which I've already found, 8 meters per second, divided by the time, which is 4 seconds. 16 divided by 4 are 4 newtons. So C is the right answer. When an increase in speed doubles the momentum of a moving body, remember momentum is equal to m times v. If I double the momentum by an increase of speed, that means I've doubled the speed. Then the kinetic energy is going to be 1/2 mv squared. If I double the speed here, that quadruples the kinetic energy. So the kinetic energy more than doubles. Bouncy rubber ball and a bean bag, each the same mass, fall to the floor by the same height. Which of these statements about the force imparted is true? The rubber ball imparts a greater force. You know, the bean bag falls and it just stops. But the rubber ball, this is the bean bag, this is the rubber ball, it falls down, goes, and then comes back up. So the change in momentum for the rubber ball is bigger than the change in momentum for the bean bag. And because it has a bigger change in momentum, since F is equal to delta P over delta T, because this is big, that means this is big. It has a bigger force. Here, convert this 8.3 revolutions to radians per second. All right, do that, I get 52 radians per second. Between midnight and 3 a.m., midnight right here goes to 3 a.m. over here. The hour hand has a displacement of 90 degrees. That's also pi over 2 radians. And recognize too that it's in the clockwise direction, so it's negative pi over 2. Boy swings a 2 kilogram stone in a horizontal circle with a radius of 3 meters. Stone breaks when the tangential velocity of the stone is 4 meters per second. What tension in the string will cause it to break? Okay, so the tension is the centripetal force, mv squared over r. That's going to be 2 kilograms times v, 4 meters per second, squared divided by 3 meters. 32 divided by 3 is going to be b, 11. Object is at rest. It accelerates at 3 revolutions per second squared. has an angular displacement of 24 revolutions, and I want to know what is the angular velocity after it rotates through that displacement. Two things you need to do here. You need to say that theta is equal to 1/2 alpha t squared and solve for t. That's 24 is equal to 1/2 of 3t squared, and I find that t is equal to 24 divided by 1.5. Is equal to 16, so t is equal to 4.0 seconds, and then omega is equal to alpha times t. That's going to be 3 times 4, or 12 revolutions per second. So omega is equal to alpha times t, which is 12 revolutions per second. This is the speed at point P. V is equal to omega times r. Looks like I'm given omega in radians per second. That's good. Times 0.7. That's going to be 0.7 meters per second. Object is at rest. If it rotates during the time, so I know that theta is equal to 1/2 alpha t squared. If I double t, that means I quadruple theta. And then here, Chad's angular velocity is the same as Kaiz's.